So in question 9, a mass of 12 kilograms rests on a rough horizontal table and is attached by two horizontal inelastic strings to masses 10 kilograms and 4 kilograms, which hang over smooth pulleys at opposite edges of the table. The coefficient of friction between the 12 kilogram mass and the table is mu. Show that if mu is 1/4, the common acceleration of the particles will be that, and what is the least value of mu for which the particles do not move. Okay, so the first one asks us something about the common acceleration. So what I'm going to do is I'm going to ignore the fact that they've given us what the acceleration should be, and I'm going to calculate the acceleration. So I set up my system as before. I have my 10 kilogram mass with a 10g force going down and T1 going up. The acceleration is going anti-clockwise this time. My 12 kilogram mass with my T1 going to the left, T2 going to the right. My acceleration goes left because it's going anti-clockwise, which means my friction is on the right hand side. And then my 4 kilogram mass over here on the right has a 4g force going down and upwards T2. The acceleration is going up on this side. So if I'm going to start writing out the forces here, I know that I'm looking at this one here. I know that my force is mass times acceleration, so it's 10a, and it's also going to be 10g minus t1. So I can say that 10a is equal to 10g minus t1, or t1 is equal to 10g minus 10a. If I look at my middle one here, okay, well, I'm told that mu is equal to 1/4. So my normal force here is going to be 12g. My friction is mu times my normal force, so it's 1/4 times 12g, so it's 3g. My forces here are going to be T1, then I have to take away T2, and I have to take away my friction. So that's going to be T1 minus T2 minus 3g. Another way of writing the force is that it's mass times acceleration, so that's 12 times a. So I can say that 12a is equal to T1 minus T2 minus 3g. On my 4 kilogram mass, moving upwards this time, we have force is equal to 4a. Then we also have that the force is going to be T2 minus 4g here. So I can say that 4a is equal to T2 minus 4g. And it works out that T2 is equal to 4g plus 4a. So I'm going to substitute this, and I'm going to substitute this into this equation here. So I have 12a is equal to T1 minus T2 minus 3g. So 12a is equal to 10g minus 10a minus 4g minus 4a minus 3g. And all the a's on the left and all the g's on the right. And I get that a is equal to 3/26g. Now I go back and check it. And yes, that's exactly what it was supposed to be. Moving on to the next part. The least value of mu for which the particles do not move. Okay, when they're not moving, the acceleration is going to be 0. Okay, so we're going to go back up in here, and all our accelerations here are going to be, so here the acceleration is going to be 0, and here the acceleration is going to be 0, and here it's going to make no difference. Okay, so we got 12a is equal to T1, and T1 is now just 10g, minus T2, which is now just 4g, minus our friction. We don't know what the friction is because we have to work out what the friction is. So we know that 10g minus 4g is 6g, and that's our friction. What do we know about the friction? The friction is equal to mu times r. The r doesn't change. Our normal force doesn't change in this case, so it's still 12g. So 6g is equal to mu times 12g, and divide both sides by 12g, and I get that mu is equal to 1/2.